Hello. So the chemistry course, we continue with the electrochemistry. So last week we had the first lesson of electrochemistry, and you can find the recording in the Moodle. This week, the second lesson of electrochemistry. And next week we continue to combustion and flue gases. And then the last lesson will be of combustion and flue gases as well. And if there will be nobody around, most probably there will be no recap either. So just then the exam on the 27th. And Mianur's last lesson of the sustainable chemistry and circular economy will be also a self-study, and you can then do it on your own time. Okay. So electrochemistry is the topic. And I will go through some exercises next. So last time I went through the exercise for the first exercise, and now I will go through the second exercise here. So we were practicing the basics of the electrochemistry. And now we would go to a galvanic cell. So electrochemistry. And this is the second exercise. This is the book exercise 6. And we have their H or H plus and zinc. And we can look at the standard reduction potentials here. And here we have the H going to getting reduced to hydrogen gas. And then we have the zinc here before it in this potential scale. So what happens in the reaction? We have H plus there dissolved. And what would happen then if it gets reduced? We need 2 of those, H pluses, hydrogen ions, and 2 electrons to make hydrogen gas. And the standard reduction potential is 0. And then we have, so this was the left-hand electrode. And right-hand electrode, there's zinc. So there's zinc, that's solid. And what kind of reaction happens to it? It will dissolve and form zinc ions and give 2 electrons. And the standard reduction potential for this is 0.76 volts. And now we have to calculate the standard cell potential. So the standard cell potential was being calculated like this. Cathode minus the potential of the anode. So my cathode is the hydrogen. I could even write here. This was cathode. And this was anode. And I will put there my cathode, which is 0, minus the potential of anode, that was negative 0.76 volts. And I get the total cell potential of 0.76 volts. So this is also called the electromotive force, EMF. It's called also EMF. Electromotive force. My next exercise would be exercise 3, which is the exercise 9 in the book. I should indicate if the following statements or claims are correct or incorrect. When zinc is immersed in copper chloride solution, zinc ions dissolve into the solution. So I immerse zinc into copper ion solution. So I have there copper chloride, which means that I have copper and then I have 2 Cl minus there, or then copper plus. So what will happen is that the zinc will give ions, electrons to the copper because it's a base metal and copper is a noble metal. You can also see it from this series. Reduction potential series, so zinc is here and copper here. So this is true. Zinc ions dissolve to the solution. This, what happens to the zinc is that it goes to zinc ions and it gives the electrons to the copper. I didn't need to calculate now the potential for this. So I could also do that, but now now I won't do that in this part. So now I have a half cell combination of magnesium. That would be solid. And magnesium ions in solution. So I mark it the way that these half cell combinations are marked. Then I have copper ions and also solid copper there. So it's the electromotive force, which is the cell potential. Let's write it like this, electromotive force. This is the claim. And now I can calculate this. So this magnesium here is the base metal and copper is a noble metal. I'll take another pen there. I'll write it here. So this is a base metal. And this is actually noble metal. And how did I know it? Because it's, for example, in this reduction potential scale before the hydrogen. The magnesium is there. The hydrogen is there with the potential of 0. And then the copper is here or then here. So the ones that are before the hydrogen are the base metals, and the ones that are after with the positive standard reduction potentials are the noble metals. And then there's something else as well, but metals. Okay, so I just have to calculate this cell potential now. For this kind of reaction to happen, I'll still write the reaction here. So magnesium, that's solid, goes to magnesium ions and gives 2 electrons. And I check the potential from my standard reduction potential scale. And this would be minus 2.37 volts. And then the copper ions take these 2 electrons and form solid copper, and the standard reduction potential is 0.34 volts. So I can still check it from here. There was the magnesium, minus 2.37. And here, the copper plus 0.34. And then I calculate the electromotive force, which was the cell potential, which was the potential of the cathode, which is being reduced, minus the potential of the anode. So the cathode is always the one where the electrons go to, and anode the one where they leave from. And my cathode was the copper. It's being reduced, the electrons go to it. And my anode was the magnesium. And I get totally 2.71 volts there. Okay, so this was the electromotive force of this kind of cell. It's not 2, but it's 2.71. So this is not true, or not true. This what it was claimed there. Then see, chlorine is stronger oxidizing agent than bromine. I can check it from here. So here I have the arrow. Strength of oxidation agent increases. When I go downwards, this reduction potential series. And now I can find the bromine here. And then the chlorine here. This is true when I compare them. The order and also the standard reduction potential for chlorine is bigger than for bromine. True. When aluminum metal is placed in aluminum metal is placed in a HCl solution, which means that I have H plus, and then I have Cl minus. This is my hydrogen chloride solution. And the container is closed. Pressure is generated due to gas formation. So is there gas formation? And the gas that would be formed would be the hydrogen gas. When I check from this standard reduction potential scale, I can see that the aluminum is here before the hydrogen. So it will actually reduce the hydrogen to hydrogen gas. So true, this aluminum will reduce the hydrogen ions and hydrogen gas is being formed. Okay. Oxygen. Okay. There is this. Now I will go to the copper dissolves if it's placed in silver nitrate solution. So this would be F. Copper and silver nitrate solution. Nitrate solution, which would mean that there is silver plus and nitrate minus, and these are both in water solution. Okay, so then we have to check because these are both noble. Copper is noble. Silver also noble. But then if we check from here, the silver in solution, this is the potential here. And for copper, it's less, and it's even, if it would be, it's in this form, it's even less. So copper is less noble. True. This copper is less noble than silver. And will reduce silver. Good. Okay, so now we will go to the next topic. Which is electrolysis. Electrolysis and batteries. So electrolysis, then the Faraday's law and how the, well, the battery, this kind of battery, or how the battery is basically a battery that one can also discharge, but also charge, how it works. So you have a voltage. In electrolysis, you have a source of voltage. Then you have, again, anode and a cathode. And again, from anode, the electrons travel to the cathode. On cathode, something's being reduced. And on anode, something's being oxidized. But this is a forced reaction now. So you use this source of voltage or electric current for this chemical reaction to happen. So the basic idea of electrolysis cell, it uses electrical energy to force a chemical reaction. The reaction is not spontaneous, and external voltage is being required. So electrical energy in this case is changed to chemical energy. So basically, something that's negative goes to anode. So the anode is actually positive. It attracts the negative ions. Then they get reduced. They release the electrons. And then the electrons travel to the cathode where something is being reduced. And this wouldn't happen without this source of voltage. But an electrolysis setup needs a voltage source, for example, a battery, accumulator, or mains electricity. And also 2 electrodes, like usually the anode and the cathode, a solution, or a molten substance that contains the ions here. The electrodes must be made of a material that conducts electricity, like metal or graphite. So cathode is actually negative sign, and anode is of positive sign. So this is the vice versa from the galvanic cell. And when the electrodes are connected to the voltage source, yes, this happens. Other becomes positive, other negative. So there are of course 2 kinds of ions in the solution. The other are positive and other negative. Positive ions are called cations, like usually, and negative ones anions. And because opposite charges attract, the positive ions move to the cathode and negative ions move to the anode. Because cathode is negative, it attracts the positive ions. And when a positive ion reaches the cathode, it receives the electrons, which was called reduction. It's been reduced. So in cathode, the reduction happens. And at the anode, because it's positive, it attracts negative ions. When a negative ion reaches the anode, it gives away its electrons, which is called oxidase. Electrolysis is used, for example, in production of metals or electroplating, also hydrogen production, and chemical industry, for example, for production of chlorine and sodium hydroxide. And here's still a recap. So electrolysis cell, anode, and then that was plus sign. For example, you can have a natrium chloride, sodium chloride solution. And or even molten sodium chloride. And you can actually, like this kind of electrolysis of molten salt, molten sodium chloride, you can produce this sodium that wouldn't exist in the nature as it's on its own. So you can produce sodium metal. But you always need the voltage source, some kind of a voltage source to carry this through. Power supply. So on cathode, you have the reduction. The matter takes electrons, and on anode, the oxidation, the matter donates the electrons. So you can, for example, do silver plating like this. So you can get something that's made of a base metal, a spoon, to be silver plated by using electrolysis. The amount of the substance depends on the charge, and this is Faraday's law. So you can calculate the amount of the substance formed, for example, the amount of the silver produced on plating the spoon in amount of substance in moles with Faraday's law. And there's this Faraday's constant, and also the amount of electrons. So the amount of substance is how many moles of a substance are formed or consumed in a reaction. But here it's mainly how much we form it. Well, not a mass, but the number of particles expressed in moles. Yeah, and 1 mole was this Avogadro's constant of particles. So in 1 mole, you have huge number of atoms or ions, the particles that is being formed. And in electrolysis, the amount of substance tells how much substance is formed at the electrode, which would be the cathode. So, for example, let's see, where is our example? Here. A copper, for example, copper. The number of electrons per reaction is the Z in the law. How many electrons are needed to form 1 particle of the substance? So, for example, if copper is in this form, 2+, you need 2 electrons, obviously, to form a solid metal copper. For silver, 1, and for aluminum, 3. And this is the Z in the Faraday's law. Why is it important? Well, this Q was how much charge in coulombs is going. And Z is how many electrons are required per particle. And if many electrons are needed per atom, there's the same charge, but less substance is produced. If few electrons are needed, it's the same charge, but more substance is produced. So, for example, for silver, there was 1 electron, and for copper 2, and aluminum less. And the current, electric current, is the charge traveled in time. So to produce solid aluminum, you need quite a big amount of electric current. So it's an energy-intensive process. Yes, and 1 mole of electrons has this Faraday constant of charge. So the Faraday constant is coulombs per mole. Okay, so the current is produced by the charge. The charge by the number of electrons and this Z tells you how many electrons are needed per particle. From there, we get the amount of substance produced by the electrolysis, and then from the moles, we can calculate the mass. The amount of substance tells how much substance is being formed. The Z tells how many electrons are needed to form one particle. So electricity is then the electrons chemical reaction, and then you get the amount and the mass. So here is this copper example. I have a current of 2 ampere. The time is 30 minutes, which has to be, of course, converted to seconds. So then I start calculating the time converted to seconds. The charge you can calculate with the current that was 2 amperes and the time in seconds. And one gets the coulombs. And then the Faraday's law, amount of substance produced. One needs 2 electrons per 1 copper atom, and the Faraday's constant. And this is how this can be calculated. So charge, number of electrons per atom, and the Faraday's constant. One gets the amount of substance, which can be converted into mass. So with the current of 2 amperes, one gets a mass of 1.2 grams of copper in 30 minutes. So half an hour. This is this symbol. And then a battery. When it's discharging, it's a galvanic cell. But then, and then it converts the chemical energy into electrical energy. The reaction is spontaneous and the electrons travel from anode to cathode. So current is being produced by the battery. When you charge the battery, you need the electrolysis, where electrical energy is converted to chemical energy. And the reaction is forced by external voltage. Electrons travel in opposite directions in both of these. So discharged, anode negative and cathode positive, and charging, anode positive and cathode negative. But in anode always happens the oxidation and cathode the reduction. Here is an example of lithium-ion battery. Why is it so popular? It has high energy density. It's lightweight. You can recharge it many times, and it doesn't hasn't get this kind of memory effect. So there are basically lithium ions. It's a bit more chemically complicated system. Anyhow, during discharge, when the battery is in use, lithium ions move to anode to cathode, and electrons move through the circuit, and they power your device. So it's really releasing the energy. Chemical energy is converted into electricity. And when it's being charged, external power pushes lithium ions. They are being reduced, and energy is stored again. So when it's charged, energy is being stored. Lithium ions move here. They are being reduced. And here are the typical reactions, but I'm not gonna go through them now. But the normal potential of lithium anyway is really low. And if one checks the potential series, reduction potential this table here, then one can see that the lithium here is here with the reduction most negative reduction potential. And then there's many other features in this why you get wider good electrochemical potential. So when charging, the voltage of the charger, of course, has to be bigger than the voltage of the battery. Sufficient voltage is needed to overcome the chemical potential difference. An electric car uses a large battery, whereas hundreds or thousands of cells. And then one gets a voltage of 400 to 800 volts. Energy is stored chemically, and then it acts as galvanic cell while you're driving. So electrolysis, the electricity is needed for chemistry, or basically electrical energy converted to chemical energy. In galvanic cell, chemical energy converted to electricity. Battery works in both directions. If it's a chargeable battery, the same system works both for charging and discharging. Yeah, so the electrochemical voltage series was here. This is what we already went through. Here you can see again the base metals and the noble metals. So these are these slides made by Tilly. And here again, when you have a battery, when you have a galvanic cell, the electrons travel spontaneously from the less noble metal to the more nobler metal. Here it would be zinc and copper. And here you can see, so galvanic cell versus electrolysis cell. Galvanic cell anode negative, and the electrons travel from it to the cathode. That's positive. But in electrolytic cell, the anode is positive. So here the reduction happens, the electrons are forced to travel then to cathode. That is negative. So galvanic cell energy released by spontaneous redox reaction, it's converted to electrical energy. And electrolytic cell electrical energy is used to drive non-spontaneous redox reaction. Here's was the Daniell pair. And this was basically a galvanic cell. Here also a galvanic cell. And then a galvanic cell can be used as a fuel cell as well. In electrolysis cell, external voltage source is connected between the electrodes and electrical energy is converted into chemical energy. And here is the Faraday's law. And this then also, usually there's, of course, this efficiency. The efficiency is not 100% in this either. Aluminum is produced by electrolyzing molten aluminum oxide. For example, like this. So aluminum ions are reduced at the cathode and one gets aluminum metal. Carbon dioxide is formed at the anode. And charging the battery is electrolysis cell, like we already talked about. For example, for a lead acid battery. Corrosion is also this kind of electrochemical reaction. Chemical oxidation reactions happen. And this is usually because there's some kind of a electrical pair. For example, the iron is being corroded and it forms rust. There's different types of corrosion. You will be talking more about corrosion on some courses to come. Okay, so now we could check more exercises. So we go to the Faraday's law and we will calculate how long does it take to electrolytically deposit the following metals when the current is 50 amperes. So 1 kilogram of aluminum from aluminum oxide solution. Let's take this first. The Faraday's law can be found from the technical formulas in electrolysis calculations. This is the Faraday's law. So I will take the exercise 11, where we need the Faraday's law. Which can be found from technical formulas, page 184. And it looks like this. There is this Q, which was the charge, is current times the time is the amount of substance times the amount of electrons times the Faraday constant. And one can find all these, this all here, the amount of transferring electrons, Faraday constant, time, quantity of electricity, electric charge, and electric current. Now, this A, we want to produce 1 kilogram of aluminum from this aluminum oxide. And so 1 kilogram, we now can calculate first the amount of substance that we want to produce. The amount of substance N. So amount of substance of aluminum is mass divided by molar mass, like we learned before. And what is happening here is that I have aluminum 3 plus. I need 3 electrons, and I make aluminum metal. Okay, so the mass was 1 kilogram, which is 1,000 grams. The molar mass of aluminum is 26.98 grams per mole, which can be found from here. Oh, here it's actually 27. I have taken a bit more accurate value. This is accurate enough, but let's keep it now like this. If I calculate this through, I get 37.064 moles. Then I have the Faraday's law here. I also knew that my current was 50 ampere. And that my Faraday constant is always 96487, and this is amperes, coulombs, and mole. So this equation, current times time, amount of substance, the Z, which was the number of electrons. The Z, I can find this would be 3 for aluminum. From which time is amount of substance times the amount of electrons times Faraday's constant divided by the current. And now I can go through this. So I have the 37.064 moles times 3, which was the amount of electrons, times the Faraday's constant, 96487 mole. And then I have the current here. From this calculation, I would get a big amount of seconds, which in finally could be I get something in seconds from which I can calculate 59.6 hours. Okay, so this in the same way, one can calculate how long time does it take for copper, of 1 kilogram of copper and 1 kilogram of nickel. Moi! No ei ihan heti, kun mä tässä pidän tämmöistä nauhoitusta.
Okay.
Mutta mä tuun ihan kohta. Yes. Joo. Kiitos. And then there is this methane exercise, which goes exactly the same way. There you need the amount of electrons, but there is a couple of things that one should go through. And then the water electrolysis. These exercises I will go through in the beginning of the next lesson. So you should calculate now the exercise. This exercise, which is the exercise 11 from the book. And then these two exercises. And I will go through them in the beginning of the next lesson. Thank you for now.